Welcome to this module, Introduction to Optimal Decision Making. I am Miquel Pereira Nieto, a research associate at University of Bristol, and I will be giving this brief introduction to this topic and some methods that can be used for it. And here in this subsection, we'll start with the motivation. Why are we interested in optimal decision making, and how can we do that? Then, in the context of multi-class classification, the objective of a classifier is that given a new instance, to be able to predict to which class it belongs among a set of possible classes. Then this may be very important in certain critical applications, like in a medical diagnosis. For example, making a wrong prediction may have fatal consequences. Self-driving cars need to make decisions like brake, accelerate, or turn, depending on the objects that the car may have in front of it. Weather forecasting maybe for extreme cases like detecting if there is an earthquake or a hurricane coming. This may be have an important outcome. And finally, another example is in finances and forecast stock market prediction, for example, or portfolio optimization. These consequences may be basically economical. Then what do they have in common in all of these cases? If we want to make optimal decisions, we need to know what are the consequences of making each of the possible predictions. And usually these are costs in the case of misclassifications and gains in the case in which we make the correct prediction. Then one possible way to make optimal decisions is using cost-sensitive classification or cost-sensitive learning. We will focus in this brief introduction on this solution. But before we go there, what types of models can we use in order to make optimal decisions? Are all classifiers able to achieve that? Then let's look at some examples first. Then let's imagine on the left side that we have a model which is a black box. We don't know what it is, but it outputs something, some type of values. At the end, we make a decision. Then this type of outputs may vary depending on the type of model. And also let's consider on the right side that in order to train the model, we had some training, validation, and test set, and then we deploy this model into a new environment, in the real life environment. Then what types of models do we have? We have models that output basically one class directly, which is the class that the model is confident about. There are models that output a class and have the option of abstaining in the cases where the model may not be sure. Imagine that the sample, the instance being classified is near the decision boundary. It may be better to abstain. For example, in a medical environment, it may be more prudent to ask an expert or to run some additional tests before making a final prediction. Other models are able to output rankings on the available classes in the sense that we don't know the distance between the different classes is not meaningful, but actually there is a certain expected order on them. Then all of these examples have something in common, and it's that they can actually output optimal decisions, but they need to be trained from the beginning, considering the costs. Then during the training, validation, and test, the information on how costly it is to make any misclassification needs to be provided. Then during deployment, they will make optimal decisions if they were trained, or they will try to make optimal decisions if the context doesn't change. Basically, there are no changes on the costs, or there are no changes on the class priors. Then other methods or other models are able to output a score value. One of the most common is a super vector machine, which provides negative values usually for the negative class and positive values for the positive class. And they don't have they have an infinite support basically. Then those types of models can be adjusted to make optimal decisions even if they were trained in without considering the costs. If we have an additional validation set later on during deployment, for example, in which we can decide the best thresholds in order to make each prediction. The probability estimation is the one that we will focus on this introduction, which are models that are able to output posterior probability estimates, class posterior probability estimates. Then some examples are logistic regression, naive and artificial neural networks. They all are able to output probabilities. And there are other models that provide class counts, like decision tree, random forest, or k-nearest neighbor, to mention a few, which can be interpreted as proportions and subsequently into probabilities. And there are methods as well to adjust those probabilities to be more accurate. Then the good thing of these models is that it's not necessary to know the costs during training, validation, and tests, because they are being optimized to provide those probabilities. Then during deployment, given the probability estimates and the costs, it's possible to make optimal decisions. And what this means is also that the costs may change over time, and the optimal decision may change consequently. Similarly, if there are changes on the class priors, those predictions can be also adjusted. I just wanted to mention that there are other models that output different types of values, and I will not cover all of them because I will focus on posterior probability estimates. But some examples are possibility theory, Cradle sets, conformal predictions, and multi-label models. Some of them can actually provide posterior probabilities, and in that case, the methods that we will discuss here can be used as well. Then the references from the previous slides can be found in the description link